Hello, my name is Alekseev, and I am head of Laboratory of Polarized Research, National Research Center, Kurchatov Institute. First of all, what is scintillation? Scintillation is an example of luminescence when we have some energy deposited by radioactive particles, and then its energy is transferred to ultraviolet or visible light. Some history of scintillation detectors is very long. This is one of the first detectors used in particle physics, and namely discovery of X-rays by William Röntgen was when he used titanium platinum cyanide screen to measure electrons, and he saw that this screen is enlightened when there are no obvious electrons coming to the screen but the lamp was on. This is as old as 1895. Then there are famous Rutherford experiments when his workers Hans Geiger and Ernest Marsden worked on the scattering of alpha particles on various foils, and they used a screen from zinc sulfide, which is one of the classical inorganic scintillators. And these experiments show to us how the atom is built inside. But this was era when only a naked eye was used in a light detector. The new era started in 1948 when a photomultiplier was used with a large crystal of sodium iodide to detect gamma rays for gamma ray spectroscopy. Let's first discuss a bit what happens when particle enters the matter. We will start with a heavy charged particle, and a classical example is muon. When muon has comparatively low energy loss due to ionization and excitation of the atoms and molecules of the matter is very large and approximately proportional to 1 over beta squared. When beta grows, it diminishes, and the number which you could remember is 2 MeV over gram over square centimeter, which is minimum ionizing loss. Then there is nearly flat relative to the energy place, and then radiative losses became. These radiative losses for muon start at very high energies, like several hundred of GeV, and the loss is approximately proportional to the energy. A different thing happens for lighter particle, and the only example of lighter particle is electron. For it, radiative loss starts much earlier, at several tenths of MeV. And because you see that the energy loss is proportional to the energy goes with decaying exponential law, and we can introduce so-called radiation length x0, which is the length when energy of energetic electron becomes E times smaller. And some example of the radiation length you can see, and its range is from some parts of centimeter for heavy elements till several tens or even 100 centimeters for light elements like hydrogen. A different story comes with photons. When the photon is not much energetic, we have photoelectric effect, and a new electron is knocked out from the matter, and the photon is completely absorbed. With the energy of photon in the range of few MeV, photoelectric effect becomes very small, and we have Compton scattering when photon just loses some part of its energy and it's transferred to electron. And when the energy reaches the threshold energy for pair production became dominating. And you see, we can't see in the traces of photons directly, but we can see electrons and positrons produced by them. And finally, the most of the energy deposited in the matter goes to ionization and excitation. We will discuss our scintillators, starting with inorganic scintillators. And the thing is that mechanism for inorganic scintillators is very different from the mechanism for organic scintillators. Inorganic scintillators are insulators. In normal state, all electrons are in the valence band and no charge can travel free. When some ionization energy is deposited, we have electrons go into conduction band, and we have holes, and they travel in the crystal till they reach so-called scintillation center, which could be either intrinsic to this crystal or some defect of the crystal or some artificially added doping like thallium in sodium iodide. The main property which we like in inorganic scintillator is that we can make them with very high Z and high density, so they have short radiation lengths. Because of the travel of electrons and holes after ionization, the decay time is comparatively large, is from say 10 nanosecond to 1 microsecond. And we need a high quality single crystal. So inorganic scintillator is comparatively expensive. The light yield of inorganic scintillators is very different, and the benchmark of inorganic scintillator is sodium iodide with 40,000 photons over MeV. The scintillation in organic scintillators is quite different, as I already said. And here are some examples of most widely used scintillators: polystyrene, polyvinyltoluene, and linear alkyl benzene. You see that all these are aromatic hydrocarbon compounds, and they all have benzene ring. So the origin of scintillation in organic scintillators is CC bond in these benzene rings. But the plastic is not transparent to the light, which will be readily emitted from the levels at this bond. And so typical three-component scheme is used. The first is scintillation in base plastic, and we have doping about 1% of the primary fluor, and this fluor is quite abundant in the plastic. So a very short distance, very effective photon energy transfer happens without really light emitting. Then the first fluor emits ultraviolet light, which can travel some small distance. And we have the second fluor. The second fluor has 20 times less concentration, and light emitted by this fluor can already travel through the plastic. You see that organic scintillators are made basically from two elements, carbon and hydrogen, which are light elements, so low Z and low ρ, like density of water, big radiation lengths. All energy transfers in organic scintillator are usually rather fast, in the range of few nanoseconds, so the response is fast. And light yield of organic scintillators is approximately the same for most of the scintillators. It is approximately 1/4 of the scintillation of sodium iodide. But this is plastic or liquid which could easily be made of any shape, and liquid could be poured in large vessels. Okay, we have scintillation light. Now we need to detect it. And the most popular light sensors used now are photomultiplier tubes and silicon photomultipliers. What is photomultiplier tubes? We have a photon entering at a photocathode on which we have photoelectric effect, and we emit one electron from one photon if we are lucky. Then this electron is directed by a static electric field to the next electrode called dynode. It hits this dynode with energy about 100 eV, And this energy is enough to knock out several more electrons, which are transferred by static electric field to the next dynode, also accelerated. And then we have an avalanche. Typically, photomultiplier tubes have 8 to 12 dinodes, and we could have very large amplification, like 100 of millions. This device is low noise device. The approximate thermal noise of photomultiplier tubes is in the range of several tens hertz, and they are relatively fast. Some drawback is that to operate photomultiplier tube, we need comparatively high voltage, like 1 to 3 kilovolts. And they are extremely sensitive to magnetic field. Even the magnetic field of the Earth should be screened for correct operation of photomultiplier tube. And they are comparatively expensive because it's very precise mechanics. Another device which became very popular this century is a silicon photomultiplier. Imagine that you have a matrix of small avalanche photodiodes. And when a photon hits this diode and electron hole pair is produced, it produces an avalanche which completely discharges this cell. So all signals from all photons look the same because we have the same capacitors of the cell as the common over voltage set to them. We have high gain because this is just capacitance times over voltage. We have a good photo detection efficiency, like 40%. We don't need very high voltage like for photomultiplier tube. The typical voltage on silicon photomultiplier is well below 100 volts. It's insensitive to magnetic field, and because it's just a piece of silicon, it's relatively cheap. The drawback of silicon photomultipliers is that because any electron hole pair in the sensitive volume can produce a discharge, it has larger single pixel noise, and the room temperature is about several tens of kilohertz per millimeter squared. This limits possible size of device to tens of millimeters squared. Now let's go to some examples of how we use organic and inorganic scintillators. Inorganic scintillators with short radiation lengths are very useful for homogeneous electromagnetic colorimeters and detecting of high energy photons. Here you see an example of very much used detector created already in 20th century. This is crystal ball detector, which is a nearly complete sphere of sodium iodide crystals read out by photomultiplier tubes. The energy resolution of this device is 2.7% at 1 GeV. Another usage is for organic scintillators. First of all, this is various trigger and time-of-flight counters. We can't do electromagnetic colorimeter just with organic scintillator because it will be very large due to long radiation lengths. But we can do a sampling electromagnetic colorimeter. We can do a large volume detector filling nearly any size vessel with liquid scintillator. And there is one more exotic usage. We can do a tracking using scintillating fibers. You see in the bottom of the picture the classical way how trigger or time-of-flight counter is built. You have a plate of scintillator which has rectangular shape, and then you need to go to round shape of photocathode or photomultiplier tube, so you use a light guide. This kind of light guide is called fishtail, and it's very widely used. There are many examples of scintillator detectors usage. Let me choose two detectors connected to neutrino physics. First is Dan's experiment at Kalininskaya nuclear power plant. The detector is placed very close to industrial power reactor, and it has 1 cubic meter of solid state plastic scintillator polystyrene, And this shape is built from 2,500 scintillation plates called strips. And to read out light from these strips, we use wavelength shifting fibers in the grooves in these strips. Another example is a very large detector, which 1,000 ton of liquid scintillator, which is a Kamioka light scintillator antineutrino detector, placed in Kamioka mine in Japan, deep underground. It's 1,000 meters below the Earth's surface. And this detector has 13 meters, sphere 13 meters in diameter, which is transparent enough. So we have about 2,000 photomultipliers tube placed on the surface of the sphere for readout. Thank you very much for your attention. And the last slide depicts the very recently built detector. It started its operation last summer. This is Juno detector in China. It's 20,000 ton of linear alkaline benzol scintillator with 43,000 photomultiplier tubes readout.